Hi everyone! You thought you were going to get rid of me for the day, but not so. We left off last time at section 27.3, which we were talking about thin film interference, and so we're going to briefly review what that's all about and then look at an example. So I kept telling you that there were more and more pieces of the puzzle, so here's the whole look at the thin film puzzle. First of all, the main idea here is that if light reflects off of a thin, very, very thin film of material, you can get it to appear to be a certain color. Sometimes this is due to constructive interference of a particular wavelength, and sometimes it's due to destructive interference. So for instance, if you have white light and you get destructive interference of the blue wavelengths within that light, then what you'll see is everything else except the blue, and generally that appears to you to be yellow. So what happens is that when light strikes the thin film, some of the light bounces back and some of the light goes through. So if here's our film, a beam of light comes down and part 1 of the beam bounces back, but part 2 of the beam goes through the thin film. Just like when you look at a window, you can see outside, so you can see that some of the light is coming through the window, but you can also see your reflection. Some of the light bounces off the window. Same idea here. So then the light gets to the bottom of the thin film and it bounces off of there. And so what you get are 2 different light beams that came from the same source, but this one traveled an extra distance, and we approximate that extra distance is 2 times the thickness of the material. So if we're close to being hitting the light perpendicular, then each one of these sides is approximately equal to the thickness of the film. So that's our approximation that we make for this. So if we get, so you can imagine if this second beam, if this extra length is exactly 1 wavelength, or 2 wavelengths, or a full number multiple of wavelengths, then these 2 beams will interfere constructively. If this extra distance is exactly half a wavelength, or 3/2, or 5/2, then these will interfere destructively and cancel out. So then the next piece of the puzzle. When a light beam reflects, sometimes it reflects back the same way it was coming in, but sometimes it changes phase, just like the wave on the string. We saw when a wave on a string hits a fixed end, it reflects back inverted. So sometimes it doesn't do that. If the wave on a string coming in hits a non-fixed end, then it'll reflect back the same way it came in. So we would say there's no phase change there. So in this case we would say this is 180 degrees out of phase with the way it was, and here we have no phase change, or it's in phase with the way it was coming in. So with light, this phase change happens if the light coming in is reflecting off a surface that has a higher index of refraction. So you can think of the higher index of refraction as being like your fixed end to your rope. So for instance, if this is air has an index of about 1. And anything else is going to have an index that's higher than that. So maybe this is 1.3. So that means that at this location here, this light beam, when it bounces off, is going to change phase, and it's going to be off by a half a wavelength. Now, if that happens at both instances of reflection, then you don't have to worry about it. But if it only happens at one, then the condition for interference is exactly opposite of what you would expect. So for instance, if this index of refraction down here is, say, 1.2, then this first beam that reflects is coming from a higher, or from a lower toward a higher index, and it reflects off the material with a higher index, so it changes phase. This one, however, is hitting a material with a lower index. It's coming from a 1.3 and hitting a 1.2, so it doesn't change phase. So what we have here now are the 2 light beams became out of phase. So let's suppose we were looking at trying to get constructive interference of these light beams. In the normal case, for constructive interference, we would have the extra length traveled, which is 2 times the thickness, would have to equal a full number of the wavelength in the film. However, if you have a phase change at one surface but not the other, then this shifts by a half. So then you have to change this to 2t equals m minus 1/2 times the wavelength in the film. In other words, now they need to be off by exactly a half number of wavelengths. It should be an equals. And if you were looking at the case for destructive interference, this would have been m plus a half to start out with to get destructive interference. Then if you've got one phase change here but not at the other surface, then you would subtract that half and you would just look for something that's off by a full number of wavelengths to get destructive interference. So again, if the phase change happens at both places, you don't have to change anything. But if a phase change happens at only one of the reflection points, then you have to subtract 1/2 from your m. Okay, so the last piece of the puzzle. The wavelength changes when it enters a thin film because we said that the speed of light slows down a bit when it enters other materials. And since speed equals frequency times wavelength, and the frequency stays constant, if the speed gets smaller, the wavelength must get smaller. So we looked at the equation for that. We said the wavelength in the film is equal to, there we go, the wavelength in a vacuum divided by the index of refraction of the film. Okay, so in order to use the wavelength here, you're going to have to translate the wavelength in a vacuum into what the wavelength would be in the film. Now, if a problem gives you a wavelength for light and it doesn't specify whether that's in the film or in a vacuum, always assume that it's in a vacuum unless otherwise specified, and then you need to calculate what it is in the film. Alright, so let's look at an example here. So here we have a colored thin film of gasoline. So thin film of gasoline is floating on a puddle of water. So here's a little cross-sectional piece of that. Sunlight falls perpendicularly on the film and reflects into your eye. So this isn't shown exactly perpendicular, just so that we can show the arrows not right on top of each other. The film has a yellow hue because destructive interference eliminates the color of blue. So here's the example I was talking about where you sometimes get destructive interference causing a particular color. So again, this wavelength given here, that's going to be the wavelength in a vacuum, since it doesn't specify that that's in the film. Oops, nanometers. Okay. So the refractive indices of the blue light in gasoline and water are 1.4 and 1.33. Determine the minimum non-zero thickness of the film. Alright, so the index of refraction in the gasoline is going to be important because that's what we need to calculate the wavelength of the light in the film. The gasoline is the film. So wavelength in the film is going to be wavelength in a vacuum divided by index of refraction of the film. And that's the gasoline. So we have our wavelength in our film is going to equal 469 nanometers divided by 1.4. And I don't know why this pen is writing so poorly. I apologize for that. Okay, so if you calculate that, that gives you 335 nanometers. So the wavelength in the film is 335 nanometers. Film. Okay, so now we need to figure out, what are we trying to find? We're supposed to find the minimum non-zero thickness of the film. So we know that for destructive interference, the extra path distance traveled by the second ray is going to be 2 times the thickness of the gasoline layer. And if we want to get destructive interference, that needs to equal m plus 1/2 times the wavelength in the film. Okay, in other words, the extra distance traveled needs to be off by exactly 1/2 wavelength, or 3/2 wavelengths, or 5/2 wavelengths, and so on. Now, the other piece of the puzzle is we need to look at, is this wave changing phase when it reflects? So if it is coming from a lower toward a higher index and it's reflecting off a higher index, then it changes phase. So looking at the first ray, this reflection here, does this change phase? Yes, it does, because it's coming from 1 to 1.4. Does this one change phase? No, it does not, because it's coming from 1.4 and reflecting off 1.3. So this changes phase only in this spot. So that means now these aren't coherent sources anymore. They're off by 180 degrees, or a half wavelength. So now, in order to get destructive interference, we need this extra distance traveled to actually be a full number of wavelengths. Or another way of looking at that is you can account for a phase change at one boundary and not the other by taking your m plus a half, or if that was just m there, if you were looking at constructive, and subtracting a half wavelength. So this minus half wavelength is accounting for the phase change at the one boundary. So then, of course, these cancel each other out, and we wind up with 2 times the thickness must equal an integer number of wavelengths. So what are we finding here? The minimum non-zero thickness. So we're looking for t, and we're looking for the minimum. So the minimum would be if we start with m equals 1. So we're going to plug in m equals 1. So then we'll have t equals 1 times the wavelength in the film, 335 nanometers, divided by 2. So if you calculate that out, you get the minimum thickness to be about 168 nanometers. Okay, so I want you to stop here and look in your book at the end of chapter 27 and try problem numbers 10 through 12, 10, 11, and 12. So you should be able to do those now after looking at thin films. If you need to, go back in the book and reread this section about thin films and see if that will help you if you need help with the problems. Once you have finished problems 10 through 12, then you can move on and talk and view the video about diffraction. So those problems are on page 884 in your book.